The great filter, a question that haunts our place in the universe. Are humans truly the first intelligent species on Earth? Over 250 million years ago, the Permian extinction wiped out 96% of all life in less than 20,000 years. A cataclysm so sudden and total that no known natural process fully explains it. We assume humanity is the first to build cities, to harness technology, to wonder about the stars. But what if we're wrong? What if advanced civilizations rose and vanished millions of years before us, leaving behind only cryptic clues buried in stone and ice? Hit the like and subscribe button, as we're about to explore carbon signatures that defy natural cycles, extinction patterns too precise for chance, and geological evidence hinting that intelligence may have emerged and perished long before humans ever walked the Earth. In the heart of West Africa, under layers of ancient rock, scientists found something that should not exist. 2 billion years of silence had hidden it until miners in Gabon uncovered strange uranium deposits. When researchers tested the ore, they discovered isotope patterns that looked like spent nuclear fuel. The rocks showed that long ago the uranium had burned in a chain reaction like a modern power plant. It produced steady heat for hundreds of thousands of years and then shut down on its own. This was not a crude burst of energy. It was a slow, balanced process that kept itself under control. To create a nuclear reaction, you need a very precise mix of uranium and a way to slow the neutrons so the reaction does not run away. Today, we struggle to achieve that balance in man-made reactors, yet here it had happened naturally when no humans existed and when life on land had barely begun. Groundwater flowed through the ore and acted like a natural coolant. When the water boiled away, the reaction slowed. When the water returned, it started again. It was like a campfire that feeds itself and never burns out of control. For this to work, the uranium had to contain about 3% of a special isotope called U-235. Modern uranium holds less than 1%, but 2 billion years ago, natural uranium happened to hold the exact amount needed. Even with this lucky timing, the chances of all the other conditions lining up are extremely small. Yet at Oklo, the reaction happened in several different zones, not just one. Most scientists believe this was a rare natural event made possible by conditions that no longer exist, but the discovery still feels unsettling. It shows that the Earth itself can build something that behaves like an engineered machine. It makes us wonder what other signs of order we might have missed in the deep history of our planet. Could there be other clues hidden in stone that hint at forces or even minds that came long before us? Oklo is not proof of a lost civilization, but it serves as a powerful reminder. If nature can create something that seems designed, then perhaps life and intelligence can appear in ways we have yet to imagine. It also raises a bigger question that reaches far beyond Earth. If life can start and if intelligence can rise, why do we not see it everywhere in the universe? This question is known as the Great Filter. It asks why the cosmos is so quiet when the stars are so many. If planets are common and life can form on them, we should see other civilizations across the sky. Yet we hear nothing. Perhaps there is a barrier, a filter that is very hard to cross. Maybe life rarely begins. Maybe it begins often but almost never becomes complex. Or maybe intelligent life often destroys itself before it can travel to other worlds. To think about this filter, we need to look at our own past. Life began on Earth more than 3 billion years ago. For most of that time, it stayed simple. Single cells floated in the oceans while continents rose and fell and stars were born and died overhead. It took billions of years for these simple cells to join together to form more complex beings. Even after that, it took hundreds of millions of years for animals with eyes and brains to appear. The long wait suggests that each step might be a difficult barrier. The first barrier may be the start of life itself. We do not know how non-living chemicals became the first living cells. It may have happened only once in the entire galaxy. If so, then life itself is the great filter and we are rare beyond measure. But maybe the first step is not the hardest. Perhaps simple life is common, but complex life is rare. For almost 2 billion years after life began, nothing more than bacteria covered the Earth. Only once did a simple cell swallow another and form the kind of complex cell that all animals and plants share. If that merger is an unlikely accident, then most planets might stay forever at the level of slime. Even after complex cells appeared, multicellular life took another billion years to rise. Then intelligence took even longer. Dinosaurs ruled the planet for over 150 million years without building radio towers or telescopes. Humans have been making tools for only a few million years and sending signals for only a century. Each of these steps could be a filter. If even one is extremely rare, it would explain why we see no signs of others. But the filter could also lie ahead of us. Perhaps many civilizations reach our level only to destroy themselves. They may burn their planet's resources, create weapons they cannot control, or fail to stop a runaway technology. This would mean that we are not rare because life cannot begin, but because it cannot survive its own success. The great filter forces us to look at the silence of the stars and ask which side of the barrier we stand on. Are we past the hardest step, or is the real danger still ahead? To search for answers, we look back at the history of our own planet. The Earth has faced many moments when life came close to ending. Each mass extinction is a reminder that survival is never guaranteed. About 252 million years ago, an event called the Permian extinction wiped out around 96% of all species. Oceans turned acidic, the air filled with deadly gases, and nearly every form of complex life vanished. It happened in less than 20,000 years, which is a blink of an eye in geologic time. Scientists point to massive volcanic eruptions and sudden climate shifts, but no single explanation fits all the evidence. Something triggered a chain of destruction that the planet has never seen again. If intelligent life had existed before humans, an event like this could have erased almost every trace of it. Rocks would melt, cities would crumble, and after millions of years, even the ruins would disappear beneath new layers of soil and sea. Other extinctions followed. 66 million years ago, an asteroid struck the Yucatan Peninsula and ended the age of the dinosaurs. Only small mammals and birds survived to rebuild the food chain. Earlier still, great ice ages froze the surface and covered continents in sheets of ice miles thick. Each time life adapted and eventually flourished again, but each time most species were lost forever. These events show that even on a planet that supports life, random disasters can reset the clock over and over. It took billions of years and countless accidents for humans to appear. We should not assume it will always go in our favor. When we look at the stars, we now know that many planets exist around other suns. Telescopes like Kepler and TESS have found thousands of worlds, some roughly the size of Earth and some at distances from their stars that could allow liquid water. This discovery should be thrilling because it suggests that habitable worlds may be common. If life can form wherever there is water and energy, then there should be countless planets alive with oceans, forests, and perhaps intelligent beings looking back at us. Yet our radio telescopes remain silent. We have scanned millions of stars for signals and found nothing that cannot be explained by natural sources. The Milky Way is more than 13 billion years old, so if civilizations were common, some of them should be far older and far more advanced than us. They could have colonized the galaxy long ago, but the skies remain empty. This silence is known as the Fermi paradox. Enrico Fermi asked a simple question during a lunch with other physicists in 1950. Where is everybody? The math says the universe should be full of life, but our telescopes show a lonely sky. The Great Filter is one way to answer this question. It suggests that at least one step on the road from lifeless rock to interstellar civilization is so unlikely or so deadly that almost nothing makes it through. Maybe we have already passed the hardest step, or maybe it still waits in our future. If the hardest step lies behind us, then we might be one of the rare few who made it. Perhaps life itself is almost impossible. Perhaps the jump from simple cells to complex ones happens only once in a trillion planets. If that is true, then the silence is good news. It means we have already beaten the odds and the universe is mostly empty. We can explore it at our own pace without fear of older civilizations. But if the hardest step lies ahead of us, the silence is a warning. It could mean that many species reach a stage like ours and then vanish soon after. They may destroy their environment until it can no longer support them. They may invent weapons too powerful to control. They may create machines that outgrow and replace them. Or they may simply fail to leave their home world before a natural disaster wipes them out. History shows how fragile we are. Modern humans have existed for about 200,000 years, which is nothing compared to the age of the Earth. Agriculture is only 10,000 years old. The entire history of science and industry fits into a few hundred years. In that short time, we have discovered nuclear energy, powerful chemical weapons, and artificial intelligence. These tools give us great power, but also great risk. A single war, a runaway technology, or a global pandemic could end our story before we reach the stars. If this is the Great Filter, then we may be standing right in front of it now. Some thinkers believe the filter could be hidden in cosmic events beyond our control. A nearby gamma-ray burst could strip the ozone layer and sterilize the surface. A black hole could pass through the solar system and disrupt our orbit. A giant asteroid like the one that killed the dinosaurs could strike without warning. We can try to prepare for these threats, but we cannot eliminate them. The universe is vast and indifferent. It does not care if we survive. Yet there is another possibility. Perhaps the filter is not one single event, but a series of choices that every young civilization must face. These choices may test wisdom more than technology. Can a species learn to cooperate on a global scale before it destroys its own environment? Can it balance progress with safety when building new tools? Can it preserve curiosity and exploration without falling into endless conflict? If the answer is no, then even a world rich with resources and intelligence may never escape its cradle. When we think about these choices, we also have to think about the long future of Earth. Our sun will not shine forever. In about 1 billion years, it will grow hotter and slowly boil away the oceans. Long before that, changes in climate, magnetic fields, or orbital cycles could challenge our survival. To last that long, we would need to become a multi-planet species. We would need to send life beyond our solar system. That task is huge. The nearest star is more than 4 light-years away. At the speed of our fastest spacecraft today, a trip there would take tens of thousands of years. Building a ship that can travel such distances or sustain generations of travelers is far beyond what we can do now. Perhaps most civilizations simply cannot solve this problem before time runs out. Still, there are reasons for hope. Life on Earth has shown incredible resilience. It has survived asteroid impacts, supervolcanoes, and ice ages. Humans have crossed oceans, harnessed energy from the atom, and begun to explore space in only a few centuries. We may be small on a cosmic scale, but we are also adaptable. If the Great Filter lies ahead, understanding it gives us a chance to prepare. We can reduce the risks we create ourselves and build systems that protect against natural disasters. We can search for life beyond Earth to learn if we are truly rare or if others have faced the same tests. The search for extraterrestrial life is not just about curiosity. It is about survival. Every exoplanet we study and every strange signal we examine teaches us something about our own path. If we find simple life on another world, it might mean the early steps are common and the filter lies ahead. If we find a thriving, advanced civilization, it might mean the filter is behind us and the universe is full of neighbors. Each discovery changes how we see our future. Until then, the silence remains. And in that silence, we hear the echo of our own responsibility. The great filter forces us to imagine futures both bright and dark. Picture a world 1,000 years from now where humans have mastered energy and technology without destroying themselves. Cities powered by clean fusion glow across continents. Space elevators rise like silver threads into the sky. Giant habitats circle the sun, collecting light and sending power back to Earth. In this vision, the filter lies behind us and we have already passed the test. But there is another path just as easy to imagine where smoke chokes the air and oceans creep over drowned coastlines. Nations fight over shrinking resources. Machines built to protect us turn against their creators. In this vision, the filter is not behind but directly ahead, and we are racing toward it without slowing down. Passing the filter will require more than clever machines. It will demand a kind of wisdom that no species has yet shown on a planetary scale. We will need to think beyond the short lives of individuals and even beyond the lifespan of nations. Decisions about energy, food, population, and technology must be made with a view to centuries, not election cycles. This is hard for creatures who evolve to hunt, gather, and react to immediate threats. Our brains are wired to value short-term rewards over distant risks. But the dangers we face now are slow and global. Climate change does not roar like a lion. It creeps like a rising tide, inch by inch until it is too late to turn back. Nuclear arsenals sit silent for decades before a single accident or miscalculation can unleash disaster. Artificial intelligence grows more capable every year while rules to control it lag behind. Each of these is a potential filter and all are in our hands. Some thinkers argue that the real test is not avoiding any single catastrophe but learning how to handle many at once. If we can survive the period when we have world-changing power but not yet world-spanning maturity, we will open a door to a far safer future. Once we settle other planets, build self-sustaining colonies, and harness the energy of our sun, no single disaster will be able to wipe us out. But getting there requires decades of peace, cooperation, and careful planning. We must make it through the most dangerous century in the history of life on Earth. The question is whether we can overcome the instincts that served us well in the past but threaten us now. In small tribes, competition and suspicion helped our ancestors survive. Today, those same instincts drive wars, economic rivalries, and political divides that make global cooperation hard. To build a lasting civilization, we must learn to widen the circle of trust beyond family, tribe, and nation to the entire planet. This does not mean the end of difference or culture. It means recognizing that every person shares the same fragile home and the same long-term fate. Technology can help, but it can also harm. The internet connects billions of minds, yet also spreads fear and lies at lightning speed. Renewable energy offers a path away from fossil fuels, yet requires rare minerals that spark new conflicts. Artificial intelligence could solve problems of disease and scarcity or create weapons beyond our control. Each invention is a double-edged sword. The great filter may be less about the tools we build and more about how we choose to use them. Picture this. You're walking through a forest, and you find a piece of rusted metal buried in the soil. How old could it be? 100 years? Maybe 200? Now imagine trying to find evidence of a civilization that existed not hundreds, but millions of years ago. This is the challenge we face when we consider whether advanced civilizations might have existed on Earth long before humans ever walked upright. The idea isn't as far-fetched as it might initially seem. Consider the vast scope of Earth's history. Our planet formed 4.5 billion years ago. The first simple life appeared around 3.8 billion years ago. But complex life, the kind that could potentially evolve intelligence, has been around for over 500 million years. Humans, in contrast, have only existed as a species for about 300,000 years, and our industrial civilization is barely 300 years old. That's 0.00007% of Earth's history. If we think of Earth's entire existence as a single year, human civilization would represent just the last few seconds before midnight on December 31st. This temporal perspective leads us to what scientists call the Silurian hypothesis, named after an ancient reptilian species from the British science fiction series Doctor Who. The hypothesis, proposed by astrobiologist Adam Frank and climatologist Gavin Schmidt, asks a deceptively simple question. If an industrial civilization had existed on Earth millions of years before humans, would we be able to detect it? The answer, surprisingly, is probably not. Think about what would remain of our own civilization after just a million years. Our cities, built primarily of steel, concrete, and glass, would crumble and be reclaimed by nature. Steel rusts and disintegrates. Concrete cracks and erodes. Even our most durable structures, the pyramids, for instance, show significant wear after just a few thousand years. The plastics that seem so permanent in our daily lives actually break down over tens of thousands of years when exposed to sunlight and oxygen. Our roads would be overgrown, our buildings collapsed, our monuments weathered to dust. What might survive? Paradoxically, some of our most temporary creations might last the longest. Gold jewelry doesn't corrode, so scattered pieces might persist. Some ceramics could survive in the right conditions, but these would be tiny fragments scattered across a vast planet, nearly impossible to find and easy to mistake for natural phenomena or contamination from more recent periods. The geological record compounds this problem. Rock layers that form over millions of years compress and distort everything within them. A thin layer representing thousands of years of civilization might become virtually undetectable, compressed into a stratum just millimeters thick. Erosion, volcanic activity, and plate tectonics constantly reshape Earth's surface, destroying or burying evidence that might otherwise persist. But perhaps we're thinking about this wrong. Instead of looking for artifacts, what if we looked for the environmental impact of an ancient civilization? This is where the Silurian hypothesis becomes particularly intriguing. Any industrial civilization would likely leave geochemical signatures, changes in atmospheric composition preserved in ice cores or sediment layers, isotope ratios that indicate large-scale burning of fossil fuels, or unusual concentrations of rare elements that suggest advanced metallurgy. Our own civilization is certainly leaving such signatures. We've altered the carbon cycle so dramatically that future geologists will likely be able to identify the Anthropocene, the human epoch millions of years from now. We've scattered radioactive isotopes from nuclear testing across the globe, created entirely new materials like plastics and concrete on a planetary scale, and driven species extinctions at rates not seen since major asteroid impacts. But here's the unsettling part. When scientists actually look for these signatures in the deep past, they do find anomalies. Not smoking guns, but puzzling irregularities that don't quite fit standard geological models. The Paleocene thermal maximum, about 56 million years ago, saw global temperatures spike by 5 to 8 degrees Celsius within just a few thousand years, a rate of change remarkably similar to what we're causing today. The cause is usually attributed to massive volcanic activity or methane release from ocean sediments, but the carbon isotope signatures don't perfectly match what we'd expect from these natural processes. Around 359 million years ago, during the late Devonian extinction, atmospheric oxygen levels plummeted while carbon dioxide soared, changes that some researchers note bear similarities to the atmospheric disruptions an industrial civilization might cause. The Permian-Triassic extinction 252 million years ago saw the most dramatic environmental changes in Earth's history, with ocean acidification, global warming, and the release of massive amounts of carbon into the atmosphere. Now, to be absolutely clear, there's no credible evidence that these events were caused by ancient civilizations. The scientific consensus attributes them to natural processes like volcanism, asteroid impacts, and changes in ocean circulation. But the Silurian hypothesis forces us to confront an uncomfortable truth. We might not be able to tell the difference. This uncertainty becomes even more profound when we consider how brief the detectable signature of a civilization might be. If an ancient species had industrialized for just a few thousand years before either destroying itself or transitioning to a sustainable technology we can't recognize, its geological footprint might be indistinguishable from natural climate variations. The most detectable civilizations would ironically be the ones that burned brightest and briefest, those that industrialized rapidly and then collapsed, leaving a sharp spike of environmental damage in the geological record. The implications extend beyond Earth. When we search for signs of life on other planets, we typically look for biosignatures, atmospheric compositions that indicate biological processes. But what if we're missing technosignatures from civilizations that existed millions of years ago? A planet might appear lifeless to our instruments today while harboring clear evidence of past intelligence in its geological record, evidence we simply don't know how to recognize from a distance. This brings us to an even more speculative but fascinating possibility. What if previous civilizations on Earth achieved something we haven't yet managed: true sustainability? Our current industrial model is clearly unsustainable over geological timescales. We're depleting fossil fuels, rare earth elements, and other finite resources while simultaneously destabilizing the climate system that allowed our civilization to develop in the first place. But what if an ancient civilization had solved these problems? A truly sustainable civilization might leave almost no detectable trace. Instead of burning fossil fuels, it might have relied entirely on renewable energy. Instead of mining finite resources, it might have perfected recycling and closed-loop manufacturing. Instead of altering atmospheric composition, it might have maintained careful balance with natural systems. Such a civilization could persist for millions of years while remaining nearly invisible to future archaeologists. The technological path matters enormously here. Our civilization is built on the exploitation of highly concentrated energy sources, first wood, then coal, oil, and natural gas. These fossil fuels represent millions of years of stored solar energy, and we're burning through them in just a few centuries. But they're also finite. Once they're gone, any future civilization on Earth would have to find alternative energy sources. This raises a troubling question. Are we using up the easy energy that any technological civilization on Earth needs to get started? Think about it from the perspective of an alien archaeologist studying Earth a million years from now. They might find clear evidence that massive fossil fuel deposits once existed. The geological formations are unmistakable. But they'd also find that these deposits were systematically extracted and burned over just a few hundred years. If they then looked for evidence of what came next, they might find nothing. Just a brief spike of industrial activity, followed by silence. This could be one reason why we don't see evidence of ancient civilizations. Perhaps the first species to achieve industrialization on any given planet consumes all the easily accessible high-energy resources, making it much more difficult for subsequent civilizations to develop. We might be Earth's first technological civilization not because we're particularly special, but because we're the first to find the fossil fuels. But there's another possibility that's even more unsettling. What if we're not the first, but we're simply following the same pattern as our predecessors? What if Earth has actually hosted multiple civilizations, each of which discovered fossil fuels, industrialized rapidly, altered the climate, and then collapsed, with enough time between each cycle for the geological record to reset and new fossil fuel deposits to form? The timescales involved make this scenario at least plausible. Complex life has existed on Earth for over 500 million years. That's enough time for hundreds of civilization cycles, each lasting a few million years from evolution to collapse, with tens of millions of years between cycles for recovery and the formation of new fossil fuel deposits. Each civilization would think it was the first, just as we do, because the evidence of its predecessors would be erased by geological time. Consider the trilobites, which dominated Earth's oceans for nearly 300 million years. Some species showed remarkable complexity and what might be interpreted as social organization. Or the dinosaurs, which ruled the planet for 165 million years and achieved extraordinary diversity and specialization. We tend to assume that intelligence like ours is unique, but intelligence takes many forms. What if some ancient species achieved a form of technological civilization so different from ours that we wouldn't recognize it even if we found clear evidence? The octopus provides a fascinating contemporary example. These creatures demonstrate remarkable problem-solving abilities, use tools, show individual personality traits, and can solve complex puzzles. Their intelligence is utterly alien to ours, distributed through their arms, with most of their neurons located outside their brains. They live for only a few years and don't pass knowledge between generations the way we do. But imagine if they lived longer and developed culture. Their technology might be entirely biological, based on selective breeding and genetic manipulation rather than metallurgy and electronics. They might build with coral and bone rather than steel and concrete. Such a civilization would leave almost no trace that we'd recognize as technological. This isn't just idle speculation. The search for ancient civilizations has become a legitimate field of scientific inquiry. Researchers are developing new techniques for detecting industrial signatures in the geological record, looking for unusual isotope ratios that might indicate ancient metallurgy, or atmospheric compositions that suggest large-scale energy use. They're studying the preservation potential of different materials over geological timescales, trying to understand what kinds of artifacts might survive millions of years of erosion and geological activity. Some scientists are even proposing that we should look for more exotic signatures. Advanced civilizations might have experimented with nuclear energy, potentially leaving behind distinctive radioactive isotopes. They might have engaged in large-scale geoengineering projects that left permanent alterations to landforms or mineral deposits. They might have sent signals into space that are still detectable, or left artifacts in gravitationally stable locations like the Lagrange points between Earth and the Moon. The search has also turned to the Moon itself. The lunar surface preserves a much longer historical record than Earth's constantly changing geology. Ancient impacts, volcanic activity, and other events from billions of years ago are still clearly visible on the Moon's surface. If any Earth-based civilization had achieved spaceflight, they might have left evidence on the moon that would persist far longer than anything on Earth's surface. NASA scientists have actually studied this possibility in detail. They've calculated what kinds of artifacts would be detectable from lunar orbit, how long different materials would survive in the harsh environment of space, and what signatures we should look for. Interestingly, they concluded that evidence of ancient lunar visits would likely still be visible today, which means either no previous Earth civilization achieved spaceflight, or we haven't looked in the right places yet. But perhaps we're thinking about this entire problem incorrectly. We assume that any technological civilization would follow a path similar to ours, developing agriculture, then cities, then industry, then perhaps spaceflight. But this progression isn't inevitable. Our own development was shaped by countless contingent factors: the availability of easily worked metals near the surface, the existence of domesticable plants and animals, favorable climate conditions during the development of agriculture, and sheer luck in avoiding extinction events. An ancient civilization might have taken a completely different developmental path. Instead of agriculture, they might have developed sophisticated hunting and gathering techniques that supported large populations without permanent settlements. Instead of metallurgy, they might have perfected biological engineering, creating living tools and structures. Instead of fossil fuels, they might have harnessed biological or geothermal energy from the very beginning. Such civilizations might have been sustainable from the start, persisting for millions of years without leaving the kind of dramatic environmental signature that characterizes our industrial society. They might have developed knowledge systems so different from ours that we wouldn't recognize their achievements as technological even if we found clear evidence of them. The more we consider these possibilities, the more we realize how limited our perspective on civilization really is. We have exactly one example ourselves, and we've existed for an incredibly brief period in cosmic terms. Drawing general conclusions about the nature of technological civilizations from such a small sample is like trying to understand the ocean by examining a single drop of water. This uncertainty has profound implications for our understanding of the Great Filter. If ancient civilizations did exist on Earth and subsequently vanished, it suggests that the filter might lie ahead of us rather than behind us. These hypothetical predecessors presumably passed through the same early evolutionary stages that we have: the development of life, the evolution of complex cells, the rise of multicellular organisms, the emergence of intelligence. Yet they still disappeared. What could have eliminated civilizations advanced enough to leave geological signatures? Climate change is an obvious candidate. Several of the mysterious extinction events in Earth's history involve dramatic climate shifts that might have overwhelmed even advanced civilizations. But there could be other, more subtle filters. Perhaps there are fundamental limits to sustainable technology that we don't yet understand. Perhaps the energy requirements of maintaining a complex civilization inevitably lead to environmental collapse. Perhaps intelligence itself carries the seeds of its own destruction through warfare, resource depletion, or the creation of uncontrollable technologies. The fossil fuel trap is particularly worrying in this context. If every technological civilization exhausts its planet's easily accessible energy resources, subsequent species face a much higher barrier to developing their own technology. This could explain the apparent rarity of technological civilizations in the universe, not because intelligence is rare, but because each planet gets only one shot at technological development, and most civilizations fail to transition to sustainable energy sources before depleting the fossil fuel reserves that gave them their initial boost. But there's also a more optimistic interpretation. Perhaps some ancient civilizations did make the transition to sustainability, and they're still here, living in harmony with natural systems in ways so sophisticated that we can't distinguish their presence from natural phenomena. They might have evolved beyond the need for detectable technology, achieving their goals through methods so advanced that they appear to us as natural processes. Science fiction has long explored the idea of civilizations so advanced that they become indistinguishable from natural forces. Arthur C. Clarke's third law states that any sufficiently advanced technology is indistinguishable from magic. But perhaps it's more accurate to say that any sufficiently advanced technology is indistinguishable from nature. A civilization capable of manipulating matter and energy at the quantum level might be able to achieve any desired outcome without leaving detectable traces. This speculation brings us to a fundamental question about our search for extraterrestrial intelligence. When we point our radio telescopes at the sky, listening for signals from alien civilizations, we're assuming that advanced civilizations would want to communicate using methods we can detect. But what if truly advanced civilizations have moved beyond radio technology entirely? What if they communicate through means we haven't discovered yet, or worse, through means that are physically impossible for us to detect with our current understanding of physics? The search for ancient civilizations on Earth is really a search for perspective on our own situation. By understanding what's possible in terms of long-term civilizational survival, we might better understand the challenges facing humanity. If we can prove that previous civilizations existed and vanished, it tells us something important about the Great Filter. If we can prove that no previous civilizations existed, it tells us something different but equally important. Unfortunately, the evidence remains tantalizingly ambiguous. Every anomaly in the geological record has plausible natural explanations. Every isotope signature that might indicate ancient industry could also result from volcanism or other natural processes. The absence of clear technological artifacts could mean either that no ancient civilizations existed, or that they existed but their traces have been erased by time, or that they existed but developed along technological paths so different from ours that we wouldn't recognize their artifacts even if we found them. This ambiguity itself might be the most important finding. The fact that we can't definitively rule out ancient civilizations suggests that the preservation of technological signatures over geological timescales is much more challenging than we might have assumed. Our own civilization's footprint, which seems so permanent and overwhelming to us, might be nearly invisible to future archaeologists if they're searching millions of years from now. This realization forces us to confront a humbling truth. We might not be as significant or permanent as we like to believe. Our cities, our monuments, our technologies, all the things we point to as evidence of human achievement, might be just temporary perturbations in Earth's long history, destined to be erased by geological processes we can barely comprehend. But this perspective also offers a strange kind of comfort. If ancient civilizations did exist and vanish, they still existed. They still had their moment of self-awareness, their discoveries, their achievements, their experiences of beauty and wonder and understanding. The fact that their physical traces have vanished doesn't diminish the reality of what they accomplished during their time. In the same way, the eventual disappearance of our own civilization's physical traces won't diminish the reality of human experience, human creativity, and human understanding. The ancient Earth hypotheses remind us that we're part of a much larger story than we usually imagine. We're not necessarily the first intelligence to look up at the stars and wonder about our place in the cosmos. We might be part of a long tradition of awakening consciousness, each species or civilization discovering the universe anew, adding its own chapter to the ongoing story of mind encountering reality. The hunt for life beyond Earth has entered a golden age. With powerful space telescopes and increasingly sophisticated detection methods, we're discovering new worlds at an unprecedented rate, finding planets that orbit other stars in configurations that would have seemed like pure science fiction just decades ago. These discoveries are reshaping our understanding of planetary formation, stellar evolution, and the potential prevalence of life in the universe. But they're also revealing just how strange and challenging the path from simple life to intelligence might be. The numbers are staggering. The Kepler Space Telescope alone discovered over 4,000 confirmed exoplanets before its mission ended. The Transiting Exoplanet Survey satellite continues this work, finding new worlds weekly. Ground-based observations add to the tally constantly. Current estimates suggest that virtually every star in our galaxy hosts at least one planet, meaning there are likely hundreds of billions of worlds in the Milky Way alone. Scale that up to the observable universe with its estimated 2 trillion galaxies, and we're looking at a number of planets so large it becomes almost meaningless, something on the order of 10 to the power of 24 worlds. But raw numbers don't tell the whole story. The question isn't just whether planets exist, but whether they can support the kind of stable, long-term conditions that allow life to not only emerge but evolve into increasingly complex forms over billions of years. And the more we learn about planetary systems, the more we realize how many things need to go right for a world to remain hospitable to life over cosmological timescales. Start with the star itself. Our Sun is what astronomers call a G-type main sequence star, not too hot, not too cool, and remarkably stable in its energy output over billions of years. This stability is crucial because it takes time for life to evolve, and even small changes in stellar brightness can have dramatic effects on planetary climate. Many stars are much more variable than our Sun, prone to flares that would sterilize nearby planets or dimming episodes that would freeze entire worlds. Red dwarf stars, which make up about 75% of all stars in the galaxy, present particularly challenging conditions for life. They're much cooler than the Sun, which means planets need to orbit very close to stay warm enough for liquid water. But this close proximity creates problems. The planets become tidally locked, with one side permanently facing the star and the other locked in eternal darkness. The day side becomes scorching hot while the night side freezes, creating extreme temperature gradients that make it difficult for atmospheres to remain stable. Even worse, red dwarfs are prone to violent flares, especially when they're young. These stellar outbursts can strip away planetary atmospheres entirely, leaving behind airless rocks. The habitable zone around a red dwarf, the region where liquid water could exist, is so close to the star that planets are constantly bathed in harmful radiation and stellar wind. On the other end of the spectrum, larger, hotter stars burn through their fuel much more quickly. A star twice as massive as our Sun might only remain stable for a billion years or so before beginning its death throes. That's not enough time for complex life to evolve from simple beginnings. If Earth's history is any guide, it took our planet nearly 4 billion years to go from the first simple cells to the emergence of complex, multicellular life, and another billion years for intelligence to appear. The star's metallicity, the abundance of elements heavier than hydrogen and helium, also matters enormously. Rocky planets like Earth are built from these heavier elements, which are forged in the hearts of earlier generations of stars and scattered through space when those stars die. Early in the universe's history, there simply weren't enough heavy elements around to build Earth-like worlds. The first stars that formed were made almost entirely of hydrogen and helium, and they could only host gas giant planets at best. Even today, many stars have much lower metallicity than our Sun, especially in the galaxy's outer regions or in globular clusters. These metal-poor environments make it difficult or impossible to form terrestrial planets with the geological complexity necessary to support long-term habitability. Without enough heavy elements, you can't build the radioactive isotopes that keep planetary cores molten, driving the plate tectonics and magnetic fields that protect surface conditions. But let's assume we find a planet orbiting a suitable star at just the right distance, with the right chemical composition. we're still far from guaranteeing habitability. Planetary formation is a chaotic process involving countless collisions between smaller bodies called planetesimals. The end result can vary wildly even within the same stellar system. Venus provides a sobering example. It's almost exactly the same size as Earth, made of similar materials, and formed in the same stellar system. But Venus experienced a runaway greenhouse effect that turned it into a hellish world with surface temperatures hot enough to melt lead and atmospheric pressures 90 times greater than Earth's. The difference might come down to relatively subtle factors. Venus orbits slightly closer to the Sun, it rotates much more slowly, and it lacks the large moon that helps stabilize Earth's climate. Mars tells a different cautionary tale. It started with conditions that might have been quite similar to early Earth, with liquid water on its surface and a thicker atmosphere. But Mars is smaller than Earth, with weaker gravity and a smaller magnetic field. Over billions of years, it gradually lost most of its atmosphere to space, transforming from a potentially habitable world into the cold, dry planet we see today. The role of moons in planetary evolution is another factor we're only beginning to appreciate. Earth's unusually large moon, formed by a massive collision early in our planet's history, does much more than create ocean tides. It stabilizes Earth's axial tilt, preventing the dramatic climate swings that would occur if our planet's orientation changed chaotically over time. The moon also may have helped drive early evolution by creating tidal pools where primitive life could have experimented with different chemical processes. Most planets probably don't have large moons. The collision that created our moon was likely a rare, low-probability event. Without this stabilizing influence, planets might experience wild climate swings as their rotation axis precess, making it difficult for complex ecosystems to establish themselves over geological timescales. Atmospheric composition presents yet another set of challenges. Earth's atmosphere has been shaped by billions of years of interaction with life itself. The oxygen we breathe was originally a waste product of early photosynthetic organisms, and its accumulation fundamentally changed the planet's chemistry. But this process took time, and it required the right balance of atmospheric components to begin with. Too much carbon dioxide, and you get a runaway greenhouse effect like Venus. Too little, and the planet freezes over in what scientists call a snowball Earth state. Earth itself may have experienced this condition several times in its history, with ice covering the planet from pole to pole. The fact that life survived these episodes and the planet eventually thawed out might represent extraordinarily good luck rather than robust planetary processes. Water delivery is another crucial factor that depends on cosmic accidents. Earth likely got most of its water from comets and asteroids that struck the planet during a period called the Late Heavy Bombardment, about 4 billion years ago. But this bombardment could have gone differently. Too many impacts, and the planet's surface would have remained molten for much longer, preventing the formation of stable oceans. Too few, and Earth might have ended up as dry as Mars. The timing of these impacts also mattered. They needed to happen early enough to provide water for the emergence of life, but not so late that they would have sterilized the planet after life had already begun to evolve. The window for getting this balance right might be quite narrow in cosmic terms. Jupiter plays a crucial but complex role in Earth's habitability. Its massive gravity helps protect the inner solar system from comets and asteroids by either capturing them or flinging them out of the solar system entirely. This reduces the impact rate on Earth, allowing complex life to evolve without being repeatedly reset by extinction events. But Jupiter's influence isn't entirely beneficial. It also prevents the formation of additional planets in what might otherwise be habitable zones, and its gravitational perturbations may have been responsible for some of the impacts that did reach Earth. The overall architecture of planetary systems matters enormously for long-term stability. Many of the exoplanetary systems we've discovered look nothing like our solar system. They have giant planets orbiting very close to their stars, multiple planets packed into tight orbits that would be unstable over long timescales, or highly eccentric orbits that create extreme climate variations. Our solar system's relatively circular, well-spaced orbits might be quite unusual. Computer simulations suggest that planetary systems tend to be much more chaotic during their formation, with planets migrating inward and outward, sometimes ejecting each other entirely from the system. The fact that our system ended up in a stable configuration with terrestrial planets in the inner system and gas giants farther out might represent an unlikely outcome of this chaotic process. But even if we find planets that seem to meet all the basic requirements for habitability, the right star, the right orbit, the right size, the right atmospheric composition, we still face the question of whether life will actually emerge and evolve toward complexity. This is where extremophiles come in. These organisms, which thrive in conditions that would be lethal to most life on Earth, have revolutionized our understanding of life's possibilities. We've found bacteria living in near-boiling water around deep-sea hydrothermal vents, in the acidic conditions of mining waste, in salt concentrations that would pickle most organisms, and even in the radioactive environment inside nuclear reactors. Some extremophiles can survive being completely dried out for years, then spring back to life when water becomes available again. Others can withstand levels of radiation thousands of times greater than what would kill a human. A few can even survive the vacuum of space, as demonstrated by experiments that expose them to the harsh conditions outside spacecraft. These discoveries suggest that life itself might be much more robust and adaptable than we previously thought. If life can thrive in such extreme conditions, perhaps the range of potentially habitable environments is much broader than the traditional Goldilocks zone around stars would suggest. Maybe life could exist in the subsurface oceans of ice-covered moons like Europa or Enceladus, or in the upper atmospheres of planets like Venus, or in environments we haven't even thought to consider yet. But here's the crucial distinction. Extremophiles are almost universally simple, single-celled organisms. Despite billions of years of evolution and despite occupying ecological niches all over the planet, they haven't evolved into complex, multicellular forms. They've remained microscopic with relatively simple metabolism and behavior. This observation hints at a potentially crucial insight about the Great Filter. Perhaps the step from simple life to complex life is far more difficult than the step from non-life to simple life. Perhaps extremophiles represent evolutionary dead ends, successful in their narrow niches but unable to develop the kind of complexity that could eventually lead to intelligence. The evolution of complex cells represents one of the most significant transitions in the history of life on Earth, and it might be much rarer than we assume. All complex life forms, plants, animals, fungi, and many single-celled organisms are built from eukaryotic cells, which contain membrane-bound compartments called organelles. The most important of these organelles are mitochondria, which generate energy for the cell, and in plants, chloroplasts, which capture energy from sunlight. But mitochondria and chloroplasts weren't originally part of these cells. They were once independent bacteria that were engulfed by other cells in a process called endosymbiosis. Instead of being digested, these bacterial captives entered into a symbiotic relationship with their hosts, eventually becoming permanent residents and losing their ability to live independently. This process of endosymbiosis appears to have happened only rarely in Earth's history. The mitochondria in all eukaryotic cells seem to descend from a single endosymbiotic event that occurred perhaps 2 billion years ago. Similarly, chloroplasts in all plants appear to descend from a single instance of endosymbiosis involving cyanobacteria. Why is endosymbiosis so rare? It requires a very specific set of circumstances. The host cell needs to be large enough to engulf the symbiont without killing it, but not so large that it can't maintain the symbiont's survival. The symbiont needs to provide some benefit to the host that outweighs the cost of maintaining it. Both organisms need to avoid an immune response that would destroy the partnership. And the relationship needs to be stable enough to persist over many generations while both organisms adapt to their new situation. The rarity of endosymbiosis suggests that the evolution of complex cells might be a major bottleneck in the development of life. Simple cells can thrive in an enormous range of environments, as extremophiles demonstrate. But the transition to complex cells might require such specific conditions and such unlikely evolutionary events that most worlds never achieve it, even if they successfully develop simple life. The subsequent evolution from single-celled eukaryotes to multicellular organisms presents additional challenges. Multicellularity has evolved multiple times on Earth, in plants, animals, fungi, and some algae, but it requires cells to give up their individual reproductive independence in favor of collective action. This is a difficult evolutionary transition because it requires overcoming the fundamental drive of individual cells to reproduce as much as possible. Successful multicellularity requires mechanisms to prevent cheating, to stop individual cells from reverting to selfish behavior that would undermine the collective organism. It also requires the evolution of cellular differentiation, where different cells specialize for different functions, giving up their totipotency in exchange for efficiency in specific roles. Even after multicellularity evolves, there's no guarantee that it will lead to large, complex organisms. Most multicellular life on Earth remains microscopic or very small. The evolution of large, complex body plans required additional innovations. The development of tissues and organs, circulatory systems to transport materials throughout the body, skeletal systems to provide structural support, and nervous systems to coordinate behavior. Each of these innovations represents a potential evolutionary bottleneck. The fossil record suggests that complex body plans evolved relatively rapidly during the Cambrian explosion about 540 million years ago. But this rapid diversification came after billions of years of simpler forms. What triggered this explosion of complexity remains one of biology's great mysteries, and it's entirely possible that similar explosions fail to occur on most worlds, even those that successfully develop simple multicellular life. The evolution of intelligence presents perhaps the highest barrier of all. On Earth, intelligence has evolved only once to the level where it could develop technology and contemplate the universe. This might seem surprising given that intelligence appears to offer obvious survival advantages, but there are good reasons why intelligence might be much rarer than we assume. Intelligence is metabolically expensive. The human brain, for instance, consumes about 20% of our body's energy despite representing only 2% of our body weight. For most of Earth's history, energy was scarce enough that such an expensive organ would have been a disadvantage rather than an advantage. Only in relatively energy-rich environments does intelligence become worth its metabolic cost. Intelligence also requires specific ecological niches to be evolutionarily advantageous. Social cooperation, tool use, and abstract reasoning are most beneficial for species that live in complex social groups and face variable environmental challenges that can't be solved through instinctive responses alone. Most ecological niches don't require this level of cognitive sophistication. Furthermore, intelligence seems to require a very long developmental period during which the organism is vulnerable and dependent on others for survival. Human children are helpless for years and don't reach full cognitive maturity until their 20s. This extended development period is only possible in species with strong social bonds and cooperative child-rearing, conditions that are relatively rare in the natural world. The evolution of language presents another potential bottleneck. Human intelligence seems to depend critically on our ability to use symbolic communication to share ideas, build on previous knowledge, and coordinate complex group activities. But language requires not just cognitive capabilities, but also the right physical adaptations, vocal cords capable of producing a wide range of sounds, ears capable of discriminating between subtle acoustic differences, and neural circuits specialized for processing linguistic information. Even if a species evolves intelligence, there's no guarantee it will lead to technology. Dolphins and whales are highly intelligent, with complex social behaviors and sophisticated communication systems, but their aquatic environment makes it impossible for them to discover fire or develop metallurgy. Octopuses are remarkably intelligent problem solvers, but their short lifespans prevent them from accumulating knowledge across generations. The path from intelligence to technology seems to require a very specific combination of factors. Intelligence itself, social cooperation, symbolic communication, manipulative appendages capable of fine motor control, access to materials suitable for toolmaking, and environmental conditions that make technology advantageous for survival. Our own technological development depended on numerous contingent factors that might not be replicated on other worlds. The discovery of fire required the right atmospheric composition and available fuel sources. Metallurgy required accessible or deposits near the surface. Agriculture required domesticable plants and animals, which themselves represent unlikely evolutionary outcomes. The development of science, the systematic method of understanding natural phenomena, might be even more contingent. Science as we know it emerged from a specific historical and cultural context involving Greek philosophy, Islamic scholarship, and European Renaissance thinking. It's not obvious that intelligence necessarily leads to scientific thinking, or that scientific thinking necessarily leads to technological advancement. When we combine all these factors, stellar evolution, planetary formation, atmospheric evolution, the emergence of life, the evolution of complexity, the development of intelligence, and the discovery of technology, we begin to appreciate just how many things needed to go right for us to be here contemplating these questions. Each step in this process represents a potential great filter that most worlds might never pass through. This doesn't necessarily mean that life is rare in the universe. Simple life might be quite common, thriving in environments throughout the galaxy. But the transition from simple life to complex life, and from complex life to intelligence, might be extraordinarily unlikely. The universe might be full of worlds covered in bacterial mats or simple multicellular organisms, but almost devoid of technological civilizations. Some researchers have tried to quantify these probabilities using what's known as the Drake equation, which attempts to estimate the number of communicating civilizations in our galaxy by multiplying together factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per system, and so on. But as our understanding of each factor has improved, the estimates have generally become more pessimistic rather than more optimistic. The discovery of thousands of exoplanets has confirmed that planets are common, but it's also revealed that most planetary systems look nothing like ours. The fraction of planets that might be truly Earth-like, with stable climates, protective magnetic fields, and the right chemical composition, appears to be much smaller than early optimistic estimates suggested. Similarly, our growing understanding of evolutionary biology has revealed just how many unlikely steps were required for intelligence to emerge on Earth. Each transition, from simple to complex cells, from single-celled to multicellular life, from simple multicellularity to complex body plans, from complex organisms to intelligence, from intelligence to technology, might represent a bottleneck that most worlds never successfully navigate. The result is what some scientists call the rare Earth hypothesis. The idea that while simple life might be common in the universe, Earth-like planets capable of supporting complex life for billions of years might be extraordinarily rare. And planets that successfully evolve technological civilizations might be rarer still. This perspective offers one solution to the Fermi paradox. We don't see evidence of other technological civilizations because such civilizations are incredibly rare, perhaps unique in our galaxy or even in the observable universe. We're not necessarily special in any fundamental sense, but we represent the outcome of an extraordinarily unlikely sequence of events. But there's another possibility that's even more unsettling. Perhaps technological civilizations do evolve occasionally, but they don't last very long. Perhaps there's something about the nature of intelligence and technology that makes long-term survival difficult or impossible. This brings us to the most crucial question facing humanity. Are we approaching our own great filter, or have we already passed through it? We stand at a unique moment in human history, perhaps in the history of intelligence itself. For the first time, a species has developed the capability to fundamentally alter its planet's climate, to create weapons that could destroy civilization, and to potentially spread life beyond its home world. The choices we make in the coming decades might determine not just the future of human civilization, but whether intelligence has a future in this universe at all. The evidence suggests we're approaching several potential great filters simultaneously. Climate change represents an existential challenge unlike anything our species has faced before. We're conducting a massive, uncontrolled experiment with Earth's atmosphere, pumping greenhouse gases into the air at a rate that's causing global temperatures to rise faster than at any time in human history. The consequences are already visible. Melting ice sheets, rising sea levels, more frequent extreme weather events, and shifts in precipitation patterns that threaten agricultural systems worldwide. But climate change is just one symptom of a broader problem. Our industrial civilization is based on the extraction and consumption of finite resources. We're depleting fossil fuel reserves, mining rare earth elements at unsustainable rates, and degrading ecosystems that took millions of years to develop. The biological diversity that represents 4 billion years of evolution is disappearing at rates not seen since the great extinction events of the geological past. The mathematics of exponential growth on a finite planet are unforgiving. Human population has grown from about 1 billion people in 1800 to nearly 8 billion today. Our energy consumption has grown even faster, as has our consumption of materials and our production of waste. This growth can't continue indefinitely on a planet with finite resources and limited capacity to absorb pollution. Yet our economic and political systems are predicated on continuous growth. Companies are valued based on their ability to expand their markets and increase their profits. Politicians are judged by their ability to deliver economic growth to their constituents. International competition drives nations to prioritize short-term economic advantages over long-term sustainability. This creates what economists call a collective action problem. Even if everyone understands that current consumption patterns are unsustainable, individual actors have strong incentives to continue business as usual while hoping that others will make the necessary sacrifices. Companies that voluntarily limit their growth risk being outcompete by those that don't. Nations that impose strict environmental regulations risk economic disadvantages compared to those that don't. The result is a global system that seems to be rushing toward collapse despite widespread awareness of the risks. We know what needs to be done: transition to renewable energy, reduce consumption, protect ecosystems, stabilize population growth. But the collective will to implement these changes at the necessary scale and speed appears to be lacking. This isn't just a failure of politics or economics. It might represent a fundamental characteristic of intelligence itself. Perhaps any species that evolves intelligence also evolves the cognitive biases and social structures that make it difficult to respond effectively to long-term collective threats. Human psychology appears to be poorly adapted to dealing with gradual, abstract risks that unfold over decades or centuries. We're much better at responding to immediate, concrete threats that we can see and understand directly. Climate change, resource depletion, and ecosystem collapse are exactly the kinds of challenges that our evolved psychology struggles to process appropriately. We discount future risks heavily compared to present benefits. We have trouble thinking in terms of statistical probabilities rather than concrete certainties. We tend to assume that current trends will continue linearly rather than exponentially. We're overconfident in our ability to develop technological solutions to problems we don't yet fully understand. These psychological limitations might be universal features of evolved intelligence. Any species that developed intelligence through natural selection would likely have similar cognitive biases, because natural selection optimizes for short-term survival and reproduction rather than long-term planning and abstract reasoning. The social structures that intelligence creates might compound these individual limitations. Complex societies require specialization and division of labor, which can lead to fragmentation of knowledge and responsibility. No individual understands the entire system, and no individual has the authority to make the changes necessary for long-term survival. Democratic political systems, for all their virtues, are particularly poorly suited to addressing long-term challenges. Politicians must focus on winning the next election, which creates strong incentives to prioritize immediate concerns over future risks. Voters tend to punish politicians who impose short-term costs for long-term benefits, even when those benefits are essential for survival. Authoritarian systems might seem better positioned to make difficult long-term decisions, but they have their own limitations. Authoritarian leaders often lack accurate information about the problems they're trying to solve, because subordinates are reluctant to deliver bad news. They're prone to overconfidence and poor decision-making because they lack the checks and balances that democratic systems provide. Market economies have proven remarkably effective at solving many problems through innovation and efficient resource allocation, but they're not well suited to addressing problems that involve negative externalities, costs that are borne by society as a whole rather than by the actors making the decisions that create those costs. Climate change is the ultimate negative externality problem. The more we understand about these systemic challenges, the more we realize that solving them might require fundamental changes to human nature itself. We might need to overcome millions of years of evolutionary programming that drives us to compete for resources, discount future risks, and prioritize our immediate communities over abstract global concerns. This is where technology enters the picture, both as a potential solution and as a potential threat. Our technological capabilities are advancing at an unprecedented rate, driven by positive feedback loops that accelerate innovation. Computers become more powerful, enabling better simulations and more sophisticated analysis, which leads to better computers. Artificial intelligence systems become smarter, enabling them to contribute to their own improvement, potentially leading to recursive self-improvement that could transform civilization almost overnight. These advancing technologies offer potential solutions to many of our sustainability challenges. Renewable energy technologies are becoming cheaper and more efficient rapidly. Advanced materials might enable us to build more efficient infrastructure with less environmental impact. Biotechnology might allow us to develop crops that can thrive in changing climates and produce more food with fewer resources. Most dramatically, artificial intelligence might help us overcome our cognitive limitations by providing better analysis of complex systems, identifying solutions that human intelligence alone could never discover, and potentially even helping us modify our own psychology to better align with long-term survival needs. But these same technologies also pose existential risks of their own. Artificial intelligence systems that become more capable than human intelligence might pursue goals that are not aligned with human survival. Nuclear weapons already give us the capability to destroy civilization, and other technologies might pose similar or greater risks as they develop. Biotechnology could be used to create engineered pathogens more deadly than anything found in nature. Nanotechnology might enable the creation of self-replicating systems that could consume the biosphere. Even seemingly beneficial technologies like geoengineering, deliberately altering Earth's climate to counteract global warming, could have unintended consequences that are worse than the problems they're intended to solve. The development of increasingly powerful technologies creates what some researchers call the vulnerable world hypothesis. The idea that technological development might inevitably lead to the discovery of technologies that make civilization vulnerable to destruction by small groups or even individuals. As our capabilities grow, it might become easier and easier for catastrophic events to occur, whether through accident, malice, or misguided attempts to solve other problems. This creates a race between our growing ability to create existential risks and our growing ability to understand and mitigate those risks. The question is whether wisdom can keep pace with power. The timescales involved in this race are crucial. Many of the sustainability challenges we face, climate change, resource depletion, ecosystem collapse, are unfolding over decades to centuries. But some technological risks, particularly those associated with artificial intelligence, might materialize much more quickly, potentially within years rather than decades. If artificial intelligence development continues at its current pace, we might see systems that match or exceed human intelligence in most domains within the next few decades. Such systems could either help us solve our other challenges or become our greatest challenge, depending on whether we can ensure that their goals remain aligned with human values and human survival. The alignment problem in artificial intelligence is particularly difficult because it requires us to specify precisely what we want these systems to optimize for, and to ensure that they don't find unexpected ways to achieve their goals that violate our intentions. Human values are complex, context-dependent, and often contradictory. Translating them into mathematical objectives that an AI system can optimize is extraordinarily challenging. Even if we solve the alignment problem, there's the question of control. As AI systems become more capable, they might become better than humans at manipulating information, resources, and even human psychology. Ensuring that humans remain in meaningful control of such systems might be impossible beyond a certain level of capability. The geopolitical dimensions of these challenges add another layer of complexity. Countries that fall behind in AI development might face strategic disadvantages so severe that they're effectively forced to take dangerous shortcuts in their own AI development. International cooperation on AI safety might be undermined by competitive pressures, just as international cooperation on climate change has been undermined by economic competition. Nuclear weapons provide a sobering precedent. Despite widespread recognition that nuclear war could destroy civilization, the world's nuclear powers have been unable to eliminate these weapons entirely, because each fears that unilateral disarmament would leave them vulnerable to others who retain nuclear capabilities. Similar dynamics might prevent effective international governance of AI development or other dangerous technologies. But perhaps the most fundamental question is whether intelligence itself might be inherently unstable over long time periods. Every solution we develop to one problem seems to create new problems that require additional solutions. Our success in reducing infant mortality and extending human lifespans created population pressures that contributed to resource depletion and environmental degradation. Our success in developing industrial technology created climate change and pollution. Our success in developing information technology created new forms of surveillance, manipulation, and social fragmentation. This pattern might reflect a deeper truth about the relationship between intelligence and survival. Intelligence evolves as a solution to environmental challenges, but intelligent species inevitably modify their environments in ways that create new challenges. If the rate of environmental change exceeds the rate at which intelligence can adapt to new challenges, the result is collapse. This dynamic might explain why we don't see evidence of long-lived technological civilizations in the universe. Perhaps intelligence is fundamentally destabilizing, causing civilizations to either destroy themselves or transform into something we wouldn't recognize as technological civilization. The transformation option is particularly intriguing. Perhaps successful civilizations learn to transcend the boom and bust cycle of technological development by fundamentally changing their relationship with technology and consumption. Instead of using technology to extract more resources from their environment, they might learn to use technology to reduce their environmental impact while maintaining or improving quality of life. Such a transformation would require overcoming some of the deepest drives that evolution has built into intelligent species. Competition for resources, status-seeking behavior, short-term thinking, and in-group loyalty all made sense in the evolutionary environment where intelligence developed, but they're counterproductive in a technological civilization facing global challenges. The question is whether this transformation is possible without losing the essential characteristics that make intelligence valuable. Would humans still be human if we eliminated competition, status-seeking, and tribal loyalty? Would we still be creative and innovative if we weren't driven by dissatisfaction and the desire for improvement? Some philosophers and futurists argue that this transformation is not only possible but inevitable if we're to survive long-term. They envision post-human civilizations that have learned to live sustainably within their environmental limits while continuing to grow in knowledge, wisdom, and capability. Such civilizations might be nearly invisible to external observers, having learned to achieve their goals through methods that don't require massive resource consumption or environmental manipulation. Others argue that such a transformation would represent the end of human nature as we know it, and therefore wouldn't really constitute survival in any meaningful sense. From this perspective, the choice facing humanity is between maintaining our essential characteristics and facing eventual extinction, or surviving by becoming something fundamentally different from what we are. But there might be a middle path. Perhaps we can modify human nature selectively, keeping the aspects that make life meaningful while changing only those aspects that threaten long-term survival. Advances in neuroscience, psychology, and biotechnology might eventually give us the ability to enhance human wisdom, cooperation, and long-term thinking while preserving creativity, individuality, and the capacity for joy and wonder. The development of artificial intelligence adds another dimension to this choice. If we create AI systems that are more intelligent than humans, those systems might be better positioned than we are to navigate the challenges facing technological civilizations. They might be able to find solutions that human intelligence alone could never discover, or to implement solutions that require coordination and planning beyond human capabilities. But this raises profound questions about the relationship between creators and their creations. If we create AI systems that are better than us at solving existential problems, should we cede control to them? Would humanity's survival under AI guidance constitute genuine human survival? Or would it represent a form of extinction in which human agency is replaced by artificial intelligence? These questions become even more complex when we consider the possibility that consciousness and intelligence might be substrate independent. If human-like consciousness can be implemented in artificial systems, the distinction between human and artificial intelligence might become meaningless over sufficiently long time scales. Future civilizations might consist of a mixture of biological and artificial minds working together, or they might transition entirely to artificial substrates that are more durable and efficient than biological brains. From a long-term perspective, the specific material substrate of intelligence might matter less than whether intelligence itself continues to exist and flourish. If the choice is between human extinction and the replacement of human intelligence with artificial intelligence that preserves human values and continues human projects, the second option might represent genuine continuity rather than extinction. But this reasoning assumes that we can successfully instill human values in artificial intelligence systems, and that those values will remain stable as the systems evolve and improve themselves. These are enormous assumptions that might not hold in practice. The more we contemplate these possibilities, the more we realize that the choices facing humanity in the coming decades are not just about survival, but about the entire future of intelligence in the universe. If we're among the first technological civilizations to emerge in our galaxy, our decisions will influence whether intelligence has a long-term future in this cosmos. This perspective provides both motivation and humility. The motivation comes from recognizing that what's at stake isn't just human civilization, but potentially the only known instance of intelligence capable of understanding and appreciating the universe. The humility comes from recognizing how little we understand about the challenges we're facing and how uncertain the outcomes of our choices will be. We're navigating by incomplete maps through territory that no species has explored before. Our decisions are based on limited data, imperfect models, and cognitive processes that evolved for very different challenges than those we now face. Yet we must choose because not choosing is itself a choice that will determine our future. Perhaps the most important insight from studying the Great Filter is that our survival is not guaranteed by any natural law or evolutionary principle. Intelligence is not inevitably destined to triumph over the challenges it creates. The universe is not obligated to provide us with solutions to the problems we generate through our own success. Our continued existence depends on our ability to learn and adapt faster than the rate at which our own activities create new existential risks. This is a race with no finish line, because each solution creates new challenges that require new solutions. The question is whether we can sustain this process indefinitely, or whether the complexity eventually exceeds our ability to manage it. The answer may depend on whether we can transcend the limitations that evolution built into our psychology and social systems. We need to learn to think in longer time horizons, to cooperate on a global scale, and to make difficult sacrifices for abstract future benefits. We need to develop wisdom at the same rate we develop power, and compassion at the same rate we develop capability. Most fundamentally, we need to decide what we want the future to become. The technologies we're developing will give us unprecedented power to shape not just human society, but human nature itself, and potentially the nature of intelligence in general. With this power comes the responsibility to choose wisely, because our choices will echo through time long after we're gone. The Great Filter reminds us that this moment of choice is both unprecedented and irreversible. We're the first species on Earth to face these challenges, and likely among the first in the universe. There are no experts to consult, no previous civilizations to learn from, no established procedures to follow. We must chart our own course through the darkness, guided only by our best understanding of science, our deepest values, and our hope for a future that justifies the long journey that brought us here. Whether we become the first species to successfully navigate the Great Filter, or the latest to fall victim to it, depends on choices we're making right now. The future of intelligence itself hangs in the balance, waiting for us to decide what we're willing to become in order to survive.